If you're asked to compare two houses and decide which one uses energy more efficiently, your first thoughts might be solar panels, insulation, or perhaps the quality of the windows. But the reality is that the outcome can be determined before construction even begins. The deciding factor is the building's shape. This principle is among the most neglected aspects of passive design. Once understood, it changes the way buildings are viewed forever. A structure designed to cooperate with natural forces rather than fight them begins with its form. Building form refers to the overall three-dimensional configuration of a structure, including its footprint, height, and degree of compactness. Form is not merely a visual choice, it is governed by physics. Every exterior surface of a building, whether wall, roof, or floor, interacts directly with outdoor conditions. Heat constantly moves through these surfaces. As a result, a building with more exterior area compared to its internal volume will experience greater heat transfer between indoors and outdoors. Architects evaluate this relationship using a measurement known as the surface-to-volume ratio, or SVR. The calculation is straightforward. It compares the total exposed surface area of a building to its total enclosed volume. Consider two buildings that each contain exactly 200 cubic meters of interior space. One is shaped as a compact cube. The other stretches into a long, narrow rectangle while maintaining the same internal volume. Although both provide identical usable space, the elongated rectangle exposes 40% more surface area than the cube. That increase means more walls, a larger roof area, and a greater amount of building envelope exposed to outdoor conditions. In a hot region, this translates into 40% additional heat entering the building. In a cold region, it means 40% more heat escaping from inside. From the perspective of heat transfer alone, the cube performs more efficiently. For this reason, passive house designers often examine the SVR at the earliest stages of a project. A lower SVR indicates a more compact form, and a more compact form generally delivers better thermal performance. This concept applies everywhere in the world. There's also a useful way to visualize it. Among all geometric shapes, the sphere possesses the lowest possible surface-to-volume ratio. In other words, it is the most compact form achievable. That principle helps explain why igloos are built with dome-like shapes. It also explains why traditional dwellings in cold environments are often low, compact, and rounded. Nature arrived at this solution long ago. While modern buildings are rarely constructed as perfect spheres, the underlying lesson remains unchanged. The nearer a structure comes to a compact, simple, and convex geometry, the lower its surface-to-volume ratio becomes. A lower SVR makes indoor temperatures easier to regulate through passive means. In hot, arid regions, the primary challenge is solar exposure. Intense sunlight strikes the building, while the ground sends additional heat back upward. Under these conditions, shade and thermal mass become essential. The most effective forms in this environment are compact layouts, organized around internal courtyards. The courtyard house offers an elegant response to these demands. Exterior walls contain very few openings, helping reduce heat entering from outside. At the center, the courtyard forms a shaded microclimate that remains cooler than its surroundings. After sunset, the courtyard releases stored heat toward the night sky. Cooling occurs through the building's form itself rather than through mechanical systems. Hot and humid climates present a different obstacle. The issue is not temperature alone, but the combination of heat and moisture. When the atmosphere is already saturated, the human body struggles to cool itself through perspiration. As a result, the design priority changes. Instead of focusing mainly on reducing heat gain, the goal becomes increasing air movement. For these conditions, a more elongated building shape is often preferred, aligned along the east-west axis. This arrangement places the longer elevations toward the north and south, where direct solar exposure is reduced. A narrower floor plate, generally between 6 and 8 meters in width, allows cross-ventilation to move air effectively from one side of the home to the other. Structures in hot, humid regions are frequently raised on stilts as well. Here, form operates on several levels simultaneously. The layout, the sectional profile, and the relationship to the site are all configured to encourage maximum airflow. Cold climates demand the opposite strategy. The objective is to retain heat. In these environments, compactness becomes the dominant principle. The ideal design achieves the lowest possible SVR through a simple and tightly organized form, avoiding unnecessary projections, deep recesses, and complicated geometry. The south-facing elevation serves as a collector of solar energy. Within the northern hemisphere, a building stretched slightly along the east-west axis and featuring a broad southern face can gather substantial amounts of winter sunlight through carefully planned glazing. This process is known as solar gain. When used correctly, it can greatly reduce heating demand and, in some cases, remove the need for mechanical heating systems altogether. A clear example can be found in traditional homes located in Leda, northern India. These buildings typically rise between 2 and 3 stories. Their forms are compact. South-facing walls are thick and windows are deeply recessed. Each component of the design serves a purpose. The goal is to capture as much winter sunlight as possible while shielding the interior from cold winds, all without relying on a single electric heater. Today, many residential projects favor L-shaped and U-shaped floor plans. On drawings, these layouts appear attractive. They produce visually engaging exterior forms. They also create opportunities for garden spaces and outdoor corners. The designs feel lively and distinctive. From a thermal standpoint, however, they introduce significant challenges. Every added wing, recess, notch, or projection increases the amount of exposed surface. Volume does not grow at the same rate. As a result, the surface-to-volume ratio rises sharply. In hot climates, those additional wall surfaces allow more heat to enter the building. Interior corners where walls face one another can become pockets that trap heat. In colder regions, those same areas become weak points where warmth escapes most rapidly. Another widespread belief is that taller buildings automatically perform better because they occupy less land. In highly dense urban settings, that assumption can sometimes be correct. Yet, where land is readily available and temperatures are high, a tall and narrow structure often produces a high surface-to-volume ratio. More wall and roof areas are exposed for every floor of usable space. Under those conditions, a low and broad building that incorporates effective shading and strong cross-ventilation frequently delivers superior thermal performance compared with a slender tower. The long-standing tradition of constructing low-rise buildings in hot climates was not driven by appearance. It was a direct response to environmental conditions. There is another common design mistake. It happens when building form is considered only in terms of space and not in relation to time. East-facing and west-facing walls receive sunlight during the morning and afternoon when the sun sits low in the sky. This low-angle radiation is extremely difficult to block with ordinary overhangs. Even a deep overhang offers limited protection because of the sun's position near the horizon. South-facing walls in the northern hemisphere experience a different condition. The sun reaches a higher angle, making it much easier to control summer exposure with a horizontal overhang. For that reason, a building that reduces the size of its east and west walls while increasing its north and south exposures already gains a passive performance advantage before any additional systems are installed. Building form often goes unnoticed. Most people pass by it every day without recognizing its influence. But once the principle becomes clear, it starts appearing everywhere. You begin to recognize which structures are struggling against local climate conditions and which ones are taking advantage of them. You also start noticing that many glass and steel buildings appearing throughout South Asian cities disregard these fundamental concepts. Their designs prioritize appearance and dependence on air conditioning. That represents a significant lost opportunity. The shape of a building is far more than a visual decision. It is one of the earliest and most powerful choices affecting energy performance, comfort, and the relationship between architecture and climate. If this discussion has changed the way you look at buildings, continue exploring the principles behind climate-responsive design and passive architecture to better understand how form can shape performance long before construction begins. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.